Okay, perfect. Hi, awesome. So it is a very early morning here in New York City. It's about 6:15 a.m., 6:20. And I'm here to talk to you guys about marker-based extrinsic calibration for thermal and RGB camera pairs with different calibration board materials. Um, so let's go ahead and I'll give you guys the introduction to why this is important in the first place. The need for uh, a- as folks tackle the climate crisis, we need to automate ways to assess ways to reduce GHG emissions. Uh, Buildings are one of the largest sources of greenhouse gas emissions, and in order to tackle building envelope inspection and analysis, what we need to do is automate the process of assessing those buildings. And one of the best ways to collect information that can be easily processed by something like a deep learning model is to use drones that have RGB and thermal data. Traditionally, thermal data is used to find leaks, and engineers use this all the time to find air leaks and areas of heat loss within building envelopes. And so the background behind our research was really to create a way to create RGB-T, so RGB and thermal tensors that could be input into a deep learning model for further analysis. Now, in order to do that, we had to register the RGB and thermal images in order to enable that low-level data fusion and allow for that analysis going forward. So to give you a showing of what a thermal image looks like, in case you haven't seen it before, these are two markers with a metal plate. You can see in the image on the right that there is uh, a reflection in the metal portion of it, and the portions that are opaque or white that cannot be very easily have a reflection seen in them, those are vinyl. And so these have different properties. Vinyl is highly emissive, whereas metal is highly reflective. And as a result of that, we see these differences in how they appear on a thermal camera. Previous works have explored image registration between RGB and thermal images. Most of that work has been feature-based methods. And so most of that work has been using some kind of, excuse me, most of that work has been using some kind of, um, sorry, most of that work has been using some kind of markers. And so those markers could be checkerboards, those markers could be dots, or those markers could be spatially offset checks on a board to collect RGB and thermal information, and then they would register it. There are limitations to that approach. Some of those limitations include the fact that aligning those RGB and thermal camera images is difficult because the cameras have different distortions and because there are different fields of views between the RGB and the thermal camera. There's also difficulties in finding reliable correspondences between the two modalities, between the RGB and the thermal image. And that's because if you don't use a marker-based method, it's very difficult to find accurate correspondences between RGB and thermal images because they don't have the same features. And even if you do use marker-based methods, you have to be very careful with how you choose the marker-based method, the markers, because not all markers will appear properly. So our proposed methodology addresses these limitations and provides an effective method of registering RGB and thermal images. We tested 3 different kinds of calibration boards. The goal of this was to make sure that these calibration boards were easy to reproduce, shippable, and non-technical enough that an engineer in the field would be able to produce these if necessary, or that they could be shipped to an engineer in the field easily, and they could be used in the field. The first that we tested was a cardboard and acrylic calibration board matrix. This was a very cheap way of doing it. The reason why, uh, so the cardboard and acrylic, the acrylic had squares cut into it, and the backing was the cardboard, and the front of the acrylic was actively heated to create a thermal difference between the back and the front. And we captured thermal data on this and ran it through checker corner detection algorithms to see if the algorithms could detect the corners, and they were unable to detect on this. The next calibration board type that we used was the wood and vinyl calibration board. The picture here in the corner is actually of the wood and vinyl. The wood was laser cut, and there was a vinyl backing to it. And the wood was spatially offset. And again, this was actively heated in the front. The wood was actively heated. And what we saw was that the RGB camera could always pick up the corners, but because of the spatial offset between the front and the front or the top of the wood checks and the roughly roughly half a centimeter thickness of the wood that made up those checks, sometimes the RGB algorithm would have issues determining the exact location of the corner because it would get confused with the tops and the bottoms of the wood. And so the RGB algorithm, the corner detection algorithm on the RGB had some issues, and the thermal one did also have issues because as the active heating was lost, it became more and more difficult for the corner detection algorithm to find checks on the wood. Finally, we had the metal and vinyl calibration board, and this offered the greatest and most passive calibration ability. It is both very stable and durable. The results were consistent every single time, and it could very easily be placed out into a field where a drone could be flown above it to capture data very quickly. And these pictures could be used to calibrate the RGB and the thermal, as well as register those two cameras. In terms of how we actually perform the registration, this is our methodology. The overview is that we would use April tags as common feature points between for the RGB and the thermal images as they would take a picture of the same scene. And then we would use a homography calculation normalization to accurately align the RGB and the thermal. So getting into a little bit more detail, we would capture RGB and thermal images, and then we would assess them to see what April tags existed in both the RGB and the thermal image. And then the intersection of that set would be used to create corresponding coordinate pairs. Those coordinate pairs would be homogenized into a vector of homogeneous coordinates, and then those coordinates would be centralized and had a normalization scaling applied to it to prepare it for the least squares problem. After that, we would assemble an A matrix for the least squares problem and apply singular value decomposition to calculate the homography. And then at that point, we would have the homography to go from normalized RGB to normalized thermal. And what we could then do is apply transform the images of the normalized thermal back into the normalized RGB back into the thermal space using the inverse thermal homography. But in addition to that, we also had to apply a Hadamard quotient to figure out how much to scale the RGB images by once they were in the thermal space in order to give both the RGB and the thermal the same field of view and the same scene. So once we have all that information, we could bring all of those matrices together to create a general transformation homography align the RGB and the thermal images to basically transform the RGB into the space of the thermal images. This methodology was evaluated on a data set of RGB pairs that we captured with the DJI Mavic 2 Enterprise Advanced drone. It's important that we say that we use this drone because this is a very widely used, commercially available drone used in building envelope inspections by engineers in industry. The image registration accuracy was assessed using the reprojection error between the transformed RGB images and the thermal images. And the results showed that the registration algorithm achieved an average pixel error of plus or minus 5 pixels in the Y direction and plus or minus 2 pixels in the X direction. And so this algorithm successfully aligned the RGB and thermal images and allowed for the fusion of those two modalities into RGB-T tensors. The end result being that they would have same size and the same field of view. So our methodology demonstrated that successfully align RGB and thermal images despite differences in camera characteristics, but that required the cameras to be fixed. Additionally, the algorithm performance was influenced by the distance between the cameras and the scene. And so the greater distance between the cameras and the scene improved image overlap and registration accuracy. The closer it was, the more issues there were. The calibration rig that used vinyl April tags and metal plates was the most robust and effective for thermal camera calibration. In the next few slides, we'll see a picture of what that looks like, and that will show you a little bit more about why it was so robust to see. There are limitations with the algorithm, and that would be the need that there needs to be a relatively far distance between the cameras and the scene. The closer that the cameras are to the scene, the more problematic that thermography, the more problematic the algorithm becomes, or the more error it has. And that's because the scaling normalization matrices change significantly, and we need to, and by having it closer, we'll have it be very different from the majority of normalization matrices. But what we could do is we could use Ransack to filter out the scaling normalization matrices that are significantly different. And by doing something like that, we could further improve the algorithm itself. So this proposed methodology gives a reliable solution for aligning RGB and thermal images, and shows an accurate fusion of these low-level data fusion of these two things for building envelope analysis. And so here are image results showing poor, medium, and fair image registration in that order. So here on the left, we have a very poor image registration. Then in the middle, it is a little bit better, significantly better. This would be something that we would consider okay. And then on the far right, we have the best image registration so far. And so this shows a little bit more about how it looks like when you combine thermal and RGB images together. So to sum it up, to conclude it, this methodology can be used for aligning the thermal and the RGB images for the purpose of building envelope analysis using a drone-based imaging system. We have introduced a robust calibration rig using the vinyl April tags overlaid onto a metal plate. It's something that can be shipped onto site. It's something that can be used in the field. There's no worry about damaging it, and it does not need any sort of passive or active heating. The algorithm that we use aligns RGB and thermal images with an average pixel error of 5 pixels, plus or minus 5 pixels in the Y direction, plus or minus 2 in the X direction. It's important to note that the performance is influenced by the camera to scene distance. And obviously greater distance means we have better accuracy. And this gives a practical solution for integrating RGB and thermal images in building envelope analysis. This allows for a comprehensive analysis of building envelope performance. It helps in that comprehensive analysis, and the goal of that obviously is to improve energy efficiency of buildings and thermal comfort, and overall this contributes to the field of building envelope analysis by providing a reliable methodology for RGB and thermal data. Thank you so much for your time. If you have any questions, I'm happy to take it.